Imagine a ship leaves Earth today, traveling at almost the speed of light. The crew are gone for 4 years. They eat, they sleep, they get bored. Nothing feels unusual. Their clocks tick normally, their hearts beat normally. Then they come home, and 60,000 years have passed. That's not science fiction. It's a reality we've already tested, with atomic clocks on aeroplanes and particles in tunnels underground. And it's only the first of the strange things that happen when you approach light speed. The others get much worse. Space shrinks, the stars go out, and the emptiness itself becomes deadly. Tonight, we take you from 10% of light speed to the absolute edge, one stage at a time, and showing you every terrifying thing waiting on the way up. Now get yourself comfortable, hit subscribe. We begin. Let's start with a number that never changes. 299,792,458 meters per second. That is the speed of light in empty space. In rounder terms, roughly 300,000 kilometers, about 186,000 miles, every single second. Hold that against something you can actually picture. In the time it takes you to blink, a beam of light has already circled the entire planet more than twice. And here is the first strange thing about that number. We do not measure it anymore. In October of 1983, at the 17th General Conference on Weights and Measures, the world's metrology authorities did something quietly radical. They stopped treating light speed as a quantity to be measured and started treating it as a fixed foundation. The meter was redefined as the distance light travels in 1 second, divided by 299,792,458. Think about what that reversal means. Before that decision, we used rulers to measure light. After it, we use light to measure rulers. So the number can never drift again. Build a better laser, run a more sensitive experiment, and you will not find a new value for light speed. You will simply learn that your meter stick was slightly off. The constant became the bedrock. Everything else became the thing being checked. But that decision only formalized something far older and far more disturbing. Because the reason physicists trusted that number enough to build the entire measurement system on top of it goes back to a failed experiment in a basement in Ohio. In July of 1887, Albert Michelson of the Case School of Applied Science and Edward Morley of Western Reserve University set up an instrument in the basement of a dormitory in Cleveland. Their goal was simple, and everyone expected it to work. At the time, physicists were nearly certain that light needed something to travel through. Sound needs air. Ocean waves need water. Light, they reasoned, must ripple through an invisible medium filling all of space. They called it the luminiferous ether. And if that ether existed, then Earth must be sailing through it. We are moving, after all. Right now, this planet is orbiting the Sun at about 30 kilometers per second, roughly 67,000 miles per hour. That is fast enough to carry you from New York to Los Angeles in a little over 2 minutes, and you feel absolutely nothing. So Michelson and Morley reasoned like swimmers in a river. Swim upstream and back, and the current cost you time. Swim across the current and back the same distance, and you finish sooner. Same swimmer, same effort, different answer, because the water itself is moving. Light should behave the same way. Beams sent along Earth's motion should return slightly out of step with beams sent across it. Their instrument was extraordinary. The optics rested on a slab of sandstone 1.5 meters square and 30 centimeters thick, about the size of a small dining table and heavy enough to resist the faintest tremor. That slab floated in a shallow pool of liquid mercury, so the entire apparatus could be turned smoothly without a shudder, like a stone raft on silver water. Mirrors folded the light path back and forth until each beam traveled about 11 meters, roughly the length of a bus. Then they turned it, slowly, again and again, 6 minutes to a rotation over several days, watching the interference pattern for the shift that had to be there. Nothing moved. No matter which direction they pointed, no matter what hour of the day, no matter where Earth sat in its orbit, Light came back at exactly the same speed. They published the result in November of 1887 in the American Journal of Science. Michelson considered it a failure. He had built the most sensitive optical instrument on Earth to detect something and detected nothing at all. That nothing is arguably the most important null result in the history of science. For 18 years, physicists tried to rescue the ether. They proposed that objects physically shrink as they move through it. They proposed that the ether gets dragged along by planets. Brilliant people built increasingly elaborate patches onto a theory that kept failing. Then, in 1905, a 26-year-old technical expert third class at the Swiss Patent Office in Bern did something none of them had done. He accepted the answer. Albert Einstein did not try to explain away the null result. He treated it as a fact about the universe and asked what reality would have to look like for that fact to be true. His paper, on the electrodynamics of moving bodies, reached the journal Annales de Physique on the 30th of June, 1905, and appeared in print that September. 31 pages. Written by a man with no university position, no laboratory, no research budget. His postulate was one sentence long. The speed of light in empty space is the same for every observer, always, regardless of how fast the source is moving, and regardless of how fast the observer is moving. Sit with how impossible that sounds. Stand on a train platform and watch someone on a passing train throw a ball forward. You see the ball moving at its own speed, plus the train's. Speeds add. That is common sense, and it is how the world has behaved for every human being who has ever lived. Now put a torch on that train instead. Let the train travel at half the speed of light. The passenger measures the beam leaving at light speed. You, standing still on the platform, measure that same beam at exactly the same speed, not 1.5 times. The same. Nothing added, nothing gained. The number refuses to move, and if the speed cannot change, something else must give. Speed is only distance divided by time. Hold the answer fixed and force the inputs to bend, and you are left with one conclusion. Time and space themselves must stretch and compress to protect that number. That single idea detonated 2 centuries of Newtonian certainty in 31 pages. Here is where most people misunderstand what the speed of light actually is. We tend to imagine it as a technological ceiling, a sign posted on a cosmic road, waiting for a better engine to blow past it. That picture is wrong in a way that matters. Light speed is not the speed of light. It is the speed of cause. It is the fastest rate at which anything that happens here can influence anything there. Anything without mass has no choice in the matter, and no ability to go slower. Light travels at that speed, and so do ripples in the shape of space itself. Those ripples have a name. Gravitational waves, literal distortions in the geometry. Everything sits inside, spreading outward like a shock wave through a fabric rather than a substance. And in 2017, they gave us the cleanest test we have ever had. On the 17th of August, 2017, 2 neutron stars spiraled together and collided in a galaxy called NGC 4993, roughly 130 million light-years away. The collision sent out 2 messengers at once, a burst of gravitational waves and a flash of gamma rays. Both crossed 130 million years of intergalactic space. They arrived 1 3/4 seconds apart. Sit with that gap for a moment. Both signals left the same event, at the same instant, and travelled for 130 million years. When they set out, dinosaurs were still walking on this planet. After a journey that long, they crossed the finish line, separated by less than 2 seconds. That agreement pins the speed of gravity to the speed of light to within roughly 1 part in a quadrillion being 1,000 million million. If you measured the distance from here to the Sun with that precision, your error would be about the width of 2 human hairs. Nothing that carries information has ever been observed exceeding this speed. Not in any accelerator. Not in any telescope. Not once. So the wall is real, and it is verified. Now measure ourselves against it. Voyager 1 is the farthest human object in existence. Launched in 1977, now more than 25 billion kilometers away, roughly 16 billion miles, still whispering back to us on a transmitter weaker than a refrigerator bulb. It moves at about 17 kilometers per second, 61,000 kilometers per hour, 38,000 miles per hour. That is about 0.006% of light speed. Picture a 100-meter running track. Fire a beam of light down it. In the time light crosses the full 100 meters, Voyager 1 has advanced 6 millimeters, about the thickness of a pencil. And here is the detail that makes it ache. In November of 2026, after 49 years of unbroken flight, Voyager 1 becomes the first human object to reach a distance of 1 light day from Earth. Half a century of travel to cover what light covers between one sunrise and the next. But Voyager is not our record holder. On the 24th of December, 2024, NASA's Parker Solar Probe fell through the Sun's outer atmosphere, passing just 6.1 million kilometers, 3.8 million miles, above the solar surface. At that moment, it was moving at 692,000 kilometers per hour, 430,000 miles per hour, 192 kilometers every second. At that speed, you would cross from Washington to Tokyo in under a minute. That is the fastest any object built by human hands has ever moved. It is 0.064% of light speed. Back to the 100-meter track, light crosses the whole thing. Parker, our absolute pinnacle, covers about 6.5 centimeters, roughly the length of your thumb. Now aim it at the nearest star. Alpha Centauri sits 4.37 light-years away, about 41.5 trillion kilometers, 25.8 trillion miles. At Parker's record speed, that crossing takes something close to 6,800 years. To arrive today, you would have had to launch it before writing existed, before the wheel, before the first stone of the first pyramid was cut. Here is the part that should unsettle you. That gap is not a problem of better rockets. Build an engine 10,000 times more powerful and you do not close it, because the resistance is not mechanical. The resistance is geometric. It is written into the shape of space and time themselves, and it grows the harder you push. Below about 10% of light speed, you would barely notice. Clocks run essentially normally. Distances look ordinary. Physics feels like home. Push to 50%, and time aboard measurably falls behind the universe outside, while the road ahead visibly shortens. Push to 90%, and the energy cost stops climbing and starts exploding, and the empty vacuum in front of you begins to burn. Push to 99.9%, and the thinnest gas in the galaxy, roughly 1 hydrogen atom per cubic centimeter, stops being nothing at all and becomes a stream of radiation striking your hull hard enough to kill. Push further still, and the faint afterglow of the Big Bang itself, the coldest light in existence, rises up in front of you as a wall of gamma rays. Every step closer multiplies the cost and the danger without any ceiling at all. This is a ladder. Every rung is worse than the one beneath it, and we are going to climb it, carefully, one rung at a time, all the way to the top, because the first thing that breaks as you begin the climb is not your ship, or your fuel, or your shielding. It is time. Time does not break the way a machine breaks. Nothing snaps, nothing shudders. No warning light comes on anywhere aboard your ship. Time simply stops matching everyone else's. And the entire effect, every consequence that follows from here, comes down to a single number. Physicists call it the Lorentz factor, and they write it with the Greek letter gamma. Strip away the mathematics, and gamma is something you already understand. An exchange rate. Think of currency at an airport counter. You hand over what you have, and the board on the wall decides what it converts into. Gamma is the exchange rate between the time you live through and the time everyone you left behind lives through. Standing still, the rate sits at 1. 1 second for you, 1 second for them. Fair trade. The faster you move, the more the rate turns against you. At 10% of light speed, around 30,000 kilometers per second, roughly 19,000 miles per second, gamma reaches 1.005. Your time runs 0.5% slow. Fly for a full year at that speed, and you come home about 2 days behind the calendar. Barely a rounding error. Push to 50%, and gamma climbs to 1.15. Now, for every hour the Earth experiences, you live through about 52 minutes. A single working day aboard would cost you a lunch break relative to home. At 90%, gamma reaches 2.29. A year aboard your ship equals roughly 2 years and 3 months outside. Your time is now running at less than half speed, and you have still not reached the steep part of the curve. At 99%, gamma is just over 7. 1 year aboard, 7 years outside. Leave on a 1-year voyage, and the infant you waved goodbye to is walking into a classroom when you return. And the curve is only beginning to bend. At 99.9%, gamma reaches 22.4. 1 year for you, 22 years for everyone else. You would step off your ship having aged a single year into a world that has raised an entire generation without you. At 99.99%, adding not 1%, but 0.09%, gamma jumps to 70.7. A year aboard now costs the outside world 70 years. An entire human life, start to finish, while you cross off 12 months on a calendar. Look carefully at what just happened. Going from 90 to 99% tripled the effect. Going from 99.9 to 99.99, a change so small most instruments would struggle to detect it, tripled it again. Now pushed to 99.9999999%, gamma exceeds 22,000. 1 day aboard your ship, a single sleep cycle, 1 meal, 1 shift at the controls, and 61 years have passed outside. You wake, you eat, you go back to sleep, and a person who was born as you closed your eyes is now old enough to retire. Gamma has no ceiling. Push closer to light speed and the number climbs without any limit at all. Not toward some large final value, but toward infinity. The wall does not get harder to climb as you approach it. The wall becomes infinitely tall. Now here is the detail that turns this from a curiosity into something genuinely disturbing. You would never feel any of it. For a moment, place yourself inside that ship at 99% of light speed. Your pulse beats at its normal rate. Your thoughts move at their normal speed. A cup of coffee on the console beside you cools in exactly the number of minutes it always has. Every clock aboard agrees with every other clock. Nothing anywhere in your experience registers as slow or strange or wrong, because every process inside your ship is slowed by exactly the same factor, including the processes you would use to measure the slowing: your heartbeat, your instruments, the vibrations of the atoms in your own body. Imagine waking to find that everything in your room had doubled in size overnight. The furniture, the walls, and the ruler you would reach for to check. You could never detect it from inside. Time dilation is not something you experience. It is something you discover afterward, when you come back and read the date. And this is not theory. Scientists have been measuring it for over 80 years. The first solid evidence came from the sky, and it came from a particle almost nobody outside physics has heard of. When cosmic rays, high-energy particles from deep space, strike the top of our atmosphere, they shatter atoms and produce a shower of debris. Among that debris are muons, heavier cousins of the electron and deeply unstable. A muon at rest survives about 2.2 microseconds, 2 millionths of a second, before it decays into other particles. That lifetime is the problem. Even traveling at 99.5% of light speed, an average muon covers only about 660 meters, roughly 2,160 feet, a little over half a kilometer, before it falls apart. Muons are born somewhere near 15 kilometers up. Almost none of them should ever reach the ground. In 1941, Bruno Rossi and David Hall took detectors to Echo Lake in Colorado, 3,240 meters up, about 10,600 feet, and compared their counts with measurements down in Denver, 1,600 meters lower. Far more muons survived the descent than any ordinary calculation allowed. In the early 1960s, David Frisch of MIT and James Smith of the University of Illinois made the measurement decisively. They counted muons at the summit of Mount Washington in New Hampshire, 1,917 meters, about 6,288 feet, then carried their equipment down to sea level at Cambridge, Massachusetts, and counted again. The muons were arriving in enormous excess. Their internal clocks had been stretched by a factor of roughly 9. From our position on the ground, those particles were living 9 times longer than physics permitted. From the muon's own point of view, nothing unusual happened at all. It lived its ordinary 2 microseconds, and the mountain rushed up to meet it. Cosmic rays arrive on nature's terms. Physicists wanted control. At CERN, on the border between France and Switzerland, researchers built a storage ring that could capture muons in a magnetic field and hold them circling at enormous speed. In the 1960s, running at gamma of about 12, roughly 99.7% of light speed, the trapped muons lived 12 times longer than muons sitting still, matching the prediction to about 1%. A more powerful run followed. Reported in Nature in 1977, muons circulating at a gamma of 29.33 lived an average of 64.4 microseconds instead of 2.2, 29 times longer. Predicted and measured to better than 1 part in 1,000. But muons are exotic. What about ordinary objects in the ordinary world? In October of 1971, Joseph Haffel of Washington University and Richard Keating of the US Naval Observatory did something almost absurdly direct. They loaded 4 cesium atomic clocks, each weighing about 36 kilograms, roughly 80 pounds, onto scheduled commercial airline flights and carried them around the world, first eastward with Earth's rotation, then westward against it. Then they came home and compared them to the clocks that had never left Washington. The eastbound clocks had lost 59 nanoseconds. The westbound clocks had gained 273. Relativity had predicted a loss of about 40 and a gain of about 275, and both results landed inside the margins. A nanosecond is a billionth of a second. The time light needs to cross the width of your hand. These are almost unimaginably small differences, but they were real, they were measured, and they were in the direction Einstein said they would be. 2 men bought seats for 4 clocks on a passenger jet and settled a question that had haunted physics for 66 years. You are carrying the practical consequence of this right now. Every satellite in the Global Positioning System orbits about 20,200 kilometers up, roughly 12,550 miles, moving at nearly 4 kilometers per second. Their motion slows their clocks by about 7 microseconds a day. Their altitude, where Earth's gravity is weaker, speeds those clocks up by about 45. Gravity wins the tug of war, and each satellite clock ends up running roughly 38 microseconds per day, faster than an identical clock on the ground. 38 millionths of a second sounds like nothing, but GPS finds your position by timing radio signals moving at light speed, and light crosses about 300 meters in a single microsecond. According to Richard Podge of Ohio State University, an uncorrected system would give you a wrong fix within roughly 2 minutes, and errors would pile up at about 10 kilometers, 6 miles, every single day. Within a week, the whole system would be useless. Your phone finds you because Einstein was right about moving clocks. The measurements have grown almost impossibly delicate since then. In February of 2022, a team at JILA in Boulder, Colorado, jointly run by NIST and the University of Colorado, published results in Nature. Working with a cloud of about 100,000 ultra-cold strontium atoms held in a lattice of laser light, Tobias Bothwell, Jun Ye and their colleagues measured atoms at the top of that cloud, ticking at a different rate from atoms at the bottom. The distance between them was 1 millimeter, the width of a sharp pencil tip. That particular measurement tracks gravity's effect on time rather than motions. The same underlying flexibility, approached from the other side. and it means the warping of time is no longer something we detect at mountain summits or aboard aircraft. We now detect it across the height of a grain of rice. So how far into the future has any human being actually travelled? The name usually attached to the question is Sergei Krikalev. Across 6 spaceflights between 1988 and 2005, the Russian cosmonaut accumulated 803 days in orbit, more than 2 full years circling the planet at nearly 8 kilometers per second. The result, calculated over that entire career, comes to roughly 2/100ths of a second. He returned to Earth about 0.02 seconds younger than everyone who stayed behind. The record has since moved. Oleg Kononenko passed the previous mark in 2024 and has now logged over 1,100 days in space, landing him somewhere near 25,000ths of a second. Hold that against something you can picture. A single frame of a cinema film lasts about 1/24th of a second. The greatest journey into the future any human being has ever made is shorter than 1 frame of a movie. That is our entire achievement. Everything else belongs to particles. Beneath the Franco-Swiss border, in a ring 27 kilometers around, about 16.5 miles, the Large Hadron Collider drives protons to 6.8 tera-electron volts per beam. At that energy, each proton moves at roughly 99.999999% of light speed, lapping the entire ring more than 11,000 times every second. Their gamma sits near 7,250, which means that while an hour passes for the physicists watching their screens, the protons in that tunnel experience about half a second. The people running the experiment and the particles inside it are living in measurably different rates of time in the same building, separated by a few meters of steel and vacuum. Not as a thought experiment, as an operational engineering fact that the machine has to be calibrated around. So travel into the future is not speculation. Physics permits it, engineers correct for it daily, and human beings have already done it. By 25 milliseconds, build a fast enough ship, and there is no known limit on how far forward you could go. A century, 1,000 years, the heat death of the last stars. But look carefully at the shape of that door. Every experiment ever performed shows time stretching in one direction only. Slow your clock, and the universe races ahead of you. Nothing in relativity offers the reverse. No mechanism, no configuration, no amount of energy that lets you decelerate back into a year you have already left. The future stands open and it costs only speed. The past stays sealed, and no price has ever been found that opens it. That is the first rung, and it changes something you probably assumed was fixed, because if your clock can slow while light speed refuses to change, then the distances you are crossing cannot possibly have stayed the same either. They have not. Follow the logic carefully, because the universe has left itself no way out. Speed is distance divided by time. Every observer, no matter how they move, must measure light at exactly the same speed. That is the one thing relativity will not bend. So, if your clock has slowed down, and light still crosses your ship at the usual rate, then the distance that light is crossing must have shrunk by exactly the amount your time stretched. Not approximately. Exactly. Same gamma, same number, space contracts along your direction of travel and only along your direction of travel. Sideways, nothing changes. The universe compresses like an accordion being squeezed, but only along the axis you're moving down. Everything perpendicular stays exactly as it was, and once you accept that, the map of the cosmos starts to fold. Take the nearest star system, 4.37 light-years away, 41.5 trillion kilometers, about 25.8 trillion miles. Now climb aboard a ship traveling at 99% of light speed and look forward. From your seat, that gap is no longer 4.37 light-years. Divided by a gamma of just over 7, the distance ahead of you shortens to about 0.62 light-years, roughly 7.5 light-months. So the crossing takes you about 7.5 months. Not 7.5 years, months. You could leave in spring and arrive before the following winter, having aged less than a single pregnancy. On Earth, meanwhile, 4 years and 5 months have passed. Both measurements are correct. Neither is an illusion. You genuinely spent 7 months in transit. They genuinely waited 4.5 years. Push a little harder, and the numbers become almost obscene. Our galaxy, based on current estimates from NASA and others, spans roughly 100,000 light-years across its main disk. Light itself, the fastest thing that exists, needs 1,000 centuries to cross it. At 99.99% of light speed, gamma reaches 70.7. From inside that ship, the entire Milky Way measures about 1,400 light-years, edge to edge, an entire galaxy folded down to the size of a modest neighborhood of stars. But look honestly at what that still costs. 1,400 light-years is not survivable. Crossing it would take about 14 centuries of your own life, the whole span from Charlemagne to the present day, aboard one ship. The galaxy has shrunk enormously, and it remains far beyond a human lifetime. Speed bought you an ocean. You needed a universe. Here is what almost everyone misunderstands about this. You are not traveling faster. Nothing about your engine has beaten light. In the frame of the Earth you left, you are still crawling along at 99% of the limit, and the journey still takes over 4 years. The universe simply becomes smaller ahead of you. Think of a road map printed on a rubber sheet. Nothing has changed about how fast you drive. Someone has grabbed the far edge of the sheet and pulled the destination closer. The mileage between cities is not a fixed property of the world. It depends on who is measuring and how fast they are moving when they do. Time dilation and length contraction are not two separate effects that happen to occur together. They are one geometry, seen from two angles. You cannot have one without the other, and neither can be switched off, because switching either off would change light's speed, and that is the one thing the universe forbids. But space and time bending is not the strangest part. Something else breaks, and it is much harder to accept. We treat now as a shared thing, this instant, everywhere, all at once, a single moment cutting across the whole universe, the same for every person and every star. Relativity says no such moment exists. Two events that happen simultaneously for someone on Earth do not happen simultaneously for a ship in motion, not because of signal delays, not because light takes time to arrive. Even after you correct for every delay, moving observers genuinely disagree about the order and timing of distant events. Now is not a property of the universe. Now is a property of your velocity, and the effect scales with distance. Across a room, the disagreement is unmeasurably small. Across light years, it becomes enormous. Picture yourself out at Alpha Centauri at 99% of light speed, still flying outward. Ask what is happening on Earth at this instant, and your answer places Earth roughly 4 1/3 years behind the date your family would give. Now turn the ship around. Same position, same speed, opposite direction. Your now on Earth jumps forward by about 8.5 years. You did not move. You did not wait. You changed direction, and nearly a decade of Earth's history slid across your definition of the present moment. You might reasonably suspect that this is a mathematical artifact, a bookkeeping quirk that only shows up at absurd speeds. Roger Penrose, who would later share the 2020 Nobel Prize in Physics, built an example in his 1989 book The Emperor's New Mind that makes it uncomfortably ordinary. Two people pass each other on a street, walking pace, one heading roughly toward the Andromeda Galaxy, 2.5 million light-years away, the other heading roughly away from it. Their speeds differ by a few kilometers per hour, slower than a bicycle, but stretch their planes of simultaneity out across 2.5 million light-years, and that tiny difference in angle opens into a gap of days. For one pedestrian, an event in Andromeda has already happened. For the other, walking the opposite way on the same pavement at the same instant, that event still lies in the future. Same street, same second, two different presents. This is where physics hands the problem to philosophy, and the disagreement has never been settled. In 1966, the Dutch physicist C.W. Rietdijk published a paper arguing that relativity proves determinism. A year later, the American philosopher Hilary Putnam reached a similar conclusion independently in a paper called Time and Physical Geometry. Their reasoning runs like this: if an event lies in your future but in someone else's past, and that other person is equally real and equally correct, then that future event must already exist in some sense. Extend the argument, and every moment, past, present, and future, exists together in a fixed four-dimensional structure, the block universe. Time does not flow. We simply move through a landscape that is already complete. Not everyone accepts this. The philosopher Howard Stein, in papers including his 1991 work on relativity theory and the openness of the future, argued the reasoning overreaches. In Relativity, he pointed out, the present is a strictly local concept. It cannot legitimately be stretched into a global slice across the cosmos in the way the argument requires. Others, including the physicist David Mermin, have made much the same point. Relativity tells us that simultaneity for distant events carries no built-in meaning, and a convenient geometric picture is not automatically a statement about what exists. The physics itself is not in dispute. The relativity of simultaneity has been confirmed for over a century, and nothing in these arguments questions it. What remains unresolved is what it tells us about the nature of time, whether relativity is describing reality's architecture or only constraining the language we may use to describe it. That debate is still open. Honest scientists on both sides will tell you the same. Now let's talk about what you would actually see, because here is where nearly every film about light speed gets it wrong. Length contraction is real. Measure a passing ship at 90% of light speed, and you will find it genuinely shorter, by a factor of about 2.3, as Peter Schatzschneider of TU Wien puts it. But you would never photograph it that way. In 1959, working independently, the American physicist James Terrell and the British mathematician Roger Penrose realized something everyone had missed for 54 years. A camera does not record a moment. A camera records the light that arrives at a moment, and light from different parts of a fast-moving object left that object at different times. Picture photographing a marching band from the side. Light from the back row has further to travel than light from the front row, so it must depart slightly earlier to reach your lens in the same instant. At walking pace, the band barely shifts in that sliver of time, and your photo looks perfectly normal. Now, let the band move at nearly light speed. In the interval between the back row's light departing and the front row's light departing, the whole formation has travelled a substantial distance. The back of the object appears displaced. The front appears compressed. Put those together, and the shape you capture is not a flattened object at all. It is a rotated one, a sphere flying past you at 99.9% of light speed, still photographs as a perfect sphere, not squashed, not stretched, simply turned, as though someone had spun it on its axis before the shutter opened. For 66 years, this stayed exactly what it had always been, a prediction nobody could test. To photograph it, you would need a macroscopic object moving at a serious fraction of light speed, and nothing in any laboratory on Earth comes close, so a team decided to change the other variable instead. In May of 2025, researchers from TU Wien and the University of Vienna, Dominik Hornoff, Victoria Helm, Enar de Dios Rodriguez, Thomas Juffmann, Philipp Haslinger, and Peter Schatzschneider published their results in the journal Communications Physics. They could not speed up the objects, so they slowed down the light, using laser pulses lasting a single picosecond, a trillionth of a second, and a gated camera with an exposure window of 300 picoseconds. They captured light scattered from precisely positioned objects, one thin slice at a time. Then they reassembled those slices according to the arrival times light would have had if it travelled at under 2 meters per second. 2 meters per second. Slower than you walk to the kitchen. Inside that reconstructed world, They photographed a cube at 80% of light speed and a sphere at 99.9%. The results match the prediction exactly. As Schatzschneider described it, the cube appears twisted and the sphere remains a sphere, but its north pole has moved. A century-old prediction, finally photographed. There is a deeper problem hiding underneath all of this, and it has troubled physicists since almost the beginning. In 1909, Paul Ehrenfest asked what happens when you spin a rigid disk. The rim travels along its own length, so its circumference should contract. The radius points sideways to that motion, so it should not change at all. But circumference and radius are locked together by ordinary geometry. You cannot shrink one and leave the other alone, not on a flat, rigid disk. Imagine a bicycle wheel whose rim shrinks while every spoke keeps its exact length. Something has to give, and physicists are still arguing about precisely what. Then, in 1976, John Stuart Bell sharpened a puzzle first raised by Edmund Dewar and Michael Barron. Two spaceships sit at rest, connected by a delicate thread. Both fire identical engines at the same instant with identical acceleration. From the launch frame, the gap between them never changes, so surely the thread is safe. Except the thread itself is moving, and moving things contract. The gap stays fixed, while the thread tries to shorten. The thread snaps. Bell met such resistance from a senior experimentalist that he took the question to CERN's theory division for arbitration. A canvas of opinion produced what Bell described as a clear consensus. The consensus said the thread would not break. The consensus was wrong. And beneath all of it lies the simplest problem of all. Push one end of a steel bar, and the far end cannot possibly know instantly. The push travels through the metal at the speed of sound in that material, thousands of times slower than light. Like a train where the pull moves down the couplings one carriage at a time. Perfect rigidity would mean information crossing an object instantly. Relativity forbids it. Nothing in this universe is truly rigid. Not steel, not diamond, not anything. Space bends, time slows. Now dissolves. Solid objects turn out not to be solid at all. And you have not yet paid for any of it. Everything so far has been the geometry. What happens to the shape of reality when you move? Nothing so far has been the invoice. What it actually costs to reach these speeds and hold them. That bill is coming, and the closer you get to the wall, the larger it becomes without any ceiling at all. Everyone learns the same rule at school. Double your speed and your energy goes up 4 times. Triple it and energy goes up 9. Energy climbs as the square of velocity, and that rule works beautifully for cars, for bullets, for rockets leaving Earth. That rule quietly falls apart as you approach light speed. The real relationship replaces it with something far less forgiving. The energy you must pour into a moving object is its gamma factor, -1, multiplied by that object's rest energy. And gamma, as we have seen, climbs without any ceiling, which means the price of speed does not rise as a curve, it rises as a cliff. To understand how brutal that is, you first need to know what rest energy actually means. Every object contains a quantity of energy simply for existing, locked into its mass, doing nothing, going nowhere. Einstein's most famous equation tells you how much. Its mass multiplied by the speed of light squared. Take 1 kilogram, a bag of sugar, something you can lift with 2 fingers. Convert that kilogram entirely into energy, with nothing wasted, and you release roughly 21.5 megatons of TNT, about 1,400 times the bomb that destroyed Hiroshima. Sitting in a bag of sugar, and in every other kilogram of matter in the universe, permanently. That is the unit we now have to spend. For every kilogram you want travelling at 99% of light speed, you must supply roughly 6 times that kilogram's entire rest energy. 6 bags of sugar, annihilated completely, to move 1 bag of sugar. And that assumes perfection, every joule delivered flawlessly into motion, nothing lost to heat, radiation or exhaust. No engine that has ever existed, or ever could exist, works that way. Push to 99.99%, and the bill climbs to about 70 times the rest energy of everything aboard. Every crew member, every instrument, every gram of hull. Push to light speed exactly, and the number does not become large, it becomes infinite, and that word matters more than it sounds. Infinite does not mean expensive. Infinite does not mean we need a better reactor, or a richer civilization, or another few centuries of engineering. Infinite means no quantity of energy in existence is sufficient, because the requirement grows faster than any supply can ever chase it. The wall is not made of difficulty. The wall is made of mathematics. Here physicists have been arguing for decades, not about the physics, but about the words. The older way of describing this said that an object's mass increases as it speeds up. Push something toward light speed and it grows heavier, harder to accelerate, until at light speed its mass would be infinite. Many of us learned it exactly that way. In June of 1989, the Soviet physicist Lev Kuhn published an article in Physics Today arguing that this relativistic mass should be abandoned entirely. In his view, mass is a fixed property of an object, the same for every observer, and dressing up rising energy as rising mass confuses students and obscures the theory. The response came quickly. Wolfgang Rindler, a respected relativist at the University of Texas, wrote to the same journal defending the concept. In 1991, Tom Sandin published a paper in the American Journal of Physics titled in its defense. The dispute never fully closed. Most working physicists today use invariant mass, a single unchanging value, and describe the barrier in terms of momentum and energy rising without limit. But the older language survives in classrooms and textbooks, and the argument still surfaces in physics education journals. Notice what nobody disputes. Both camps calculate identical numbers. Both predict identical experiments. Both agree the resistance grows without bound. They are arguing about the label on the wall, not about the wall. So far, we have only counted the energy the ship needs. Now comes the part that turns a hard problem into an almost absurd one. Your fuel has mass, which means before your fuel can accelerate you, it must first accelerate itself, and the fuel that accelerates that fuel must also be carried, and so on, all the way down. Think of it as a relay of porters crossing a desert. Every porter carrying water for the group must also drink. Add distance, and you do not add porters in a neat line. You add porters to carry water for the porters, then more to carry water for those. The requirement compounds. The relativistic rocket equation behaves exactly this way. Every extra kilogram costs you exponentially, not linearly. An exponential growth is the one thing human intuition consistently underestimates. Let's put actual numbers on it, using the cleanest possible case, a perfect photon drive, converting matter and antimatter into pure radiation at 100% efficiency. No engine can do this. Nothing in nature does this. Treat these figures as the absolute floor of what physics permits. The physicist John Byers maintains a widely cited calculation of exactly this scenario. Fly past Vega, 27 light-years away, without slowing down, and you need 57 kilograms of fuel for every kilogram of payload. Already severe, but conceivable. Now stop when you arrive. Deceleration is not free. Slowing down costs almost as much as speeding up, and you had to carry that braking fuel the whole way. The requirement jumps to 886 kilograms per kilogram, roughly a small car's worth of perfect antimatter fuel to deliver a single bag of sugar to Vega and bring it to rest. Go further. Travel to the center of our galaxy, 30,000 light-years away, and stop there. The figure becomes 955,000 tons of fuel for 1 kilogram of payload. About 10 fully loaded aircraft carriers annihilated perfectly to deliver something you could hold in one hand, and to reach the Andromeda Galaxy, 2 million light-years out, and stop. 4.2 thousand million tons per kilogram. Sit with the shape of that escalation. Andromeda sits roughly 74,000 times further than Vega. The fuel bill does not rise 74,000 times. It rises by a factor close to 5,000 million. That is what exponential means, and no engineering ever negotiates with it. you might reasonably object that antimatter is at least a real substance. We produce it. CERN has an entire facility devoted to it. Here is what that facility actually produces. According to CERN's own figures, running the antimatter factory non-stop for an entire year yields antiprotons carrying about 500 joules of energy in total, enough to light a 100-watt bulb for 5 seconds. 1 year of work by one of the most advanced laboratories humanity has ever built. 5 seconds of a light bulb, against a requirement of 4,000 million tons. And even if production improved by factors we cannot currently imagine, nobody knows how to store antimatter in bulk. Any container touching it is annihilated on contact. Present-day traps hold a few thousand atoms, suspended in magnetic fields, for hours at a time. So the perfect efficiency fuel we assumed for those calculations does not exist, cannot presently be made, and could not be held if it were. Every serious interstellar concept since the 1950s has been an attempt to escape this trap. Each one is ingenious. Each one carries a flaw that has never been solved. In 1958, at General Atomics in San Diego, Ted Taylor and Freeman Dyson began Project Orion. The idea was almost violent in its simplicity. Eject small nuclear bombs behind the ship and detonate them against a massive steel pusher plate, riding the shock waves forward. A plate roughly 40 meters across, about 135 feet, the width of a football pitch. An interstellar version, accelerating at 1G for 10 days, would reach about 3% of light speed, roughly 10,000 kilometers per second, 6,000 miles every second, then coast toward Alpha Centauri for 133 years. Orion was killed partly by physics and partly by treaty. The 1963 Partial Test Ban Treaty prohibited nuclear detonations in space. Then, through the 1970s, members of the British Interplanetary Society ran Project Daedalus under Alan Bond, the most thorough interstellar design study ever attempted. Their answer replaced bombs with fusion, tiny pellets of fuel ignited by electron beams, hundreds of times a second. The vehicle they designed weighed 54,000 tons, more than 100 times the mass of the entire International Space Station, and almost all of it fuel. Its reward, 12% of light speed and a journey to Barnard's star in around 50 years. But Daedalus could not stop. It was a flyby. Decades of travel for hours of observation, streaking past its target at 36,000 kilometers per second and vanishing into the dark forever. Beginning in 2009, Project Icarus revisited that design with modern engineering knowledge. The conclusion was sobering rather than encouraging. The requirements remain far beyond anything we can currently build. In April of 2016, Yuri Milner announced a different approach entirely, with Stephen Hawking beside him. Breakthrough Starshot inverts the problem. If fuel is the enemy, remove the fuel. Shrink the spacecraft to a gram, about the mass of a paperclip. Attach it to a reflective sail roughly 4 meters square and leave the power source on the ground. A phased array of lasers, kilometers wide, would fire 100 gigawatts at that sail, roughly the output of 100 large nuclear reactors, focused into a single coherent beam. For a few minutes, the sail would endure accelerations tens of thousands of times Earth's gravity. Then the beam would cut out, and the craft would coast at about 20% of light speed, 60,000 kilometers per second, 37,000 miles every second, arriving at Alpha Centauri roughly 20 years later. It remains the most credible near-term concept anyone has produced, and it carries the same wound as Daedalus. No brakes. The probe would cross 4 light years, gather data for a few hours, and be gone. One idea escaped the trap entirely, at least on paper. In 1960, Robert Bussard published a proposal in Acta Astronautica. Don't carry fuel, and don't leave it behind. Harvest it. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter. Deploy an enormous magnetic funnel ahead of the ship. Scoop that hydrogen as you fly, and fuse it for thrust. An engine that refuels itself forever, from the emptiness in front of it. Carl Sagan popularized it. Generations of physicists fell in love with it. Then people started checking the numbers. In 1988, Dana Andrews asked Robert Zubrin to calculate the drag such a magnetic scoop would create. The answer ended the dream. The drag from capturing those particles exceeded the thrust the engine could produce. The scoop was a brake pretending to be an engine. And in 2022, Peter Schatzschneider and Albert Jackson published a detailed reanalysis in Acta Astronautica, simulating the magnetic scoop configuration proposed by John Fishback in 1969. Their simulations confirmed the concept is physically possible. Then they calculated the hardware. To generate 10 million newtons of thrust, about twice the space shuttle's main propulsion, the funnel would need a diameter of nearly 4,000 kilometers, around 2,500 miles, wide enough to span a continent. But the length was the killer. The magnetic coils would have to extend roughly 150 million kilometers, 93 million miles, the distance from the Earth to the Sun. Their conclusion states it plainly. Even a civilization capable of harnessing the entire output of its own star would very likely be unable to build such a thing. Visiting the galactic center this way, within a lifetime, they wrote, is unrealizable. Out of that failure came a genuine consolation prize. Zubrin and Andrews realized that if a magnetic field creates more drag than thrust, then drag is exactly what you want at the far end of a journey. Deploy a loop of superconducting wire, let its magnetic field push against the thin plasma of interstellar space, and you have a parachute made of nothing but a field. A magnetic sail cannot launch you, but it might stop you without carrying a single gram of braking fuel. That single idea removes half the fuel bill from every one of those staggering numbers, half of a requirement measured in aircraft carriers. So here is where the accounting leaves us. The energy cost climbs without limit. The fuel cost compounds exponentially on top of it. The one perfect fuel we can name exists in quantities measured in seconds of light bulb. Every escape route, bombs, fusion pellets, ground-based lasers scooping the void, buys us a few percent of light speed at best, and usually cannot stop when it arrives. Now suppose all of it were solved. Suppose some future civilization finds the energy, builds the engine, and pushes a crude ship to 99% of light speed. They would face something none of these calculations included, because interstellar space is not empty. It holds that thin haze of hydrogen, roughly 1 atom per cubic centimeter, the finest vacuum any laboratory on Earth would envy. At walking pace, that haze is nothing at all. At 99% of light speed, it stops behaving like gas, and the emptiness in front of the ship becomes the deadliest thing in the journey. Take a cubic centimeter of interstellar space, roughly the volume of a sugar cube. Inside it, on average, sits about 1 atom of hydrogen. Some regions hold a little more. Measurements along the routes we care about suggest closer to 2. Either way, the number is almost absurdly small. Scoop up that sugar cube of the galaxy, and you would hold essentially nothing at all. Walk through it, drive through it, fly a jet through it. You would never detect its presence. But you are not walking. You are traveling at 99% of the speed of light. Here is where the physics turns against you, and it turns on a single change of perspective. From inside your ship, you are not moving. You are sitting still. Your coffee sits still. Your instruments sit still. The galaxy is moving. That thin haze of hydrogen, sparse, cold, harmless, is now streaming toward you at 99% of light speed. Every atom in your path is no longer a wisp of gas drifting through the dark. Each one is a projectile, and it is coming at you with the full energy that speed confers. The energy of each arriving atom is set by that same gamma factor, and it climbs exactly the way gamma climbs. Above half light speed, each incoming hydrogen nucleus carries more than 100 million electron volts. At 99%, it carries several thousand million. For comparison, the particles that particle physics laboratories build enormous machines to produce sit in precisely that range. Physicists spend billions of dollars and decades of engineering to generate beams like this in shielded underground halls. Your ship would not be flying through interstellar gas. Your ship would be sitting inside the beam. Oleg Semyonov, working at Stony Brook University in New York, has published a series of analyses on exactly this problem. His figures are not comforting. At speeds of 30% of light and above, the flux striking the front of your vessel exceeds 1,000 million particles per square centimetre every second. Take the area of your fingernail, 1 billion high-energy nucleons through it every second without pause. For an astronaut with no protection, the absorbed dose reaches something in the order of 10,000 rem per second. Semyonov compares that directly to standing inside the core of an operating nuclear reactor. Now place that against human biology. A whole body dose of a few hundred rem is severe. A dose of 1,000 rem is universally fatal. And the accepted safe exposure for a person is somewhere between 5 and 10 rem per year. So a single second at 30% of light speed delivers well over 1,000 years worth of a lifetime safe limit. Death would not arrive after weeks of radiation sickness. Death would arrive in a fraction of a second before anyone aboard understood that anything had changed. Even at more moderate speeds, 20 to 40% of light, Semyonov's calculations put the unprotected dose rate anywhere from hundreds to thousands of rem every second. The emptiest place in the universe becomes the most lethal environment humans have ever contemplated entering. In 2012, William Edelstein, a physicist who spent much of his career developing magnetic resonance imaging, published a paper with his son Arthur in the journal Natural Science. The title states their conclusion plainly: speed kills. They modelled a spherical vessel 10 meters across, about 33 feet, roughly the width of a house, wrapped in an aluminium hull 10 centimeters thick, weighing around 85 tons, 4 inches of solid metal. Not remotely enough. Their finding was that avoiding severe hydrogen irradiation imposes an upper speed limit somewhere near half the speed of light. And now, look at what that limit actually buys you. At 50% of light speed, your gamma factor is 1.15. Time aboard runs about 15% slower than time at home. Useful for a trip to a nearby star, utterly worthless for crossing a galaxy. Think about the cruelty of that arrangement. The entire reason to chase relativistic speed is the time dilation. The time dilation only becomes powerful above 90%, and the radiation may become unsurvivable at 50. The prize sits on the far side of a door that appears to be nailed shut, but this is genuinely contested, and honesty requires laying out both sides. Semyonov reaches a different conclusion from the Edelsteins. He argues that shielding a relativistic starship from this bombardment does not appear far beyond existing technology, that a relatively lightweight system combining a magnetic field with what he calls an electron stripper could handle the incoming flow. The Edelsteins counter that stopping or diverting this flux with material or electromagnetic shields is a daunting problem, one whose mass and energy requirements grow punishingly with speed. Semyonov's own numbers illustrate the difficulty. Up to about 30% of light speed, a titanium shield roughly 2 centimeters thick, less than an inch, might do the job. Push toward 80% and that shield must become several meters thick. And every kilogram of shielding is a kilogram you must accelerate, which drives the fuel bill back up exponentially. Where the practical ceiling actually sits, half-light speed or somewhere higher with clever engineering, remains unsettled. No one has built either shield. Both positions are argued in the published literature by serious people. What nobody disputes is that a ceiling exists, and that it lies far below the speed the mathematics would otherwise permit. Here is the specific difficulty that makes magnetic shielding so hard. A magnetic field can only push on something carrying an electric charge. Bare protons, hydrogen stripped of its electron, can be bent aside. Ionized gas can be deflected. But much of interstellar hydrogen is neutral, a complete atom, proton and electron together, with no net charge. To a magnetic field, a neutral atom is invisible. The field reaches out, finds nothing to grip, and the atom sails straight through into your hull. Semyonov's proposed answer is the electron stripper, a system that tears the electrons off incoming atoms first, converting them into charged particles the magnetic shield can then throw aside. Elegant in principle, never built and never tested at these energies, and whatever gets through does something specific and destructive to your hull. Protons burying themselves inside solid material do not simply stop. They come to rest, capture electrons, and become hydrogen gas trapped inside the metal or ceramic. Over time, that trapped gas forms bubbles. The bubbles blister the surface, the layers begin to separate. Your shield does not wear away like a stone in a river. It swells and delaminates from within, like paint lifting off wet wood. We have a detailed calculation of this, because someone ran it for a mission people are actually trying to build. In 2017, Thiem Huang, Alex Lazarian, Blakesley Burkhart, and Abraham Loeb published a study in the Astrophysical Journal on exactly what interstellar gas and dust would do to a breakthrough starshot craft moving at 20% of light speed. Their finding on gas bombardment, on the journey to Alpha Centauri, damage could reach a depth of about 0.1 millimeters in quartz, roughly the thickness of a sheet of paper. A sheet of paper sounds trivial. Remember what is being eroded. Starshot's sail is a film measured in hundreds of nanometers, a thickness perhaps 500 times thinner than that damage depth. Their work also found graphite far more resistant than quartz, which is exactly the kind of finding that shapes real engineering decisions. And that is at 20% of light speed, not 99. Gas is not the only thing out there. Interstellar dust grains are microscopic, typically a fraction of a micron, perhaps 1,000th the width of a human hair. Individually nothing, collectively a permanent hazard along every route. The same team modelled what happens when one strikes at relativistic speed. The answer is not a scratch, and not a dent. The impact deposits so much energy so quickly that the surface atoms explosively evaporate. The grain does not embed itself. It flashes both itself and a patch of your hull into vapour, leaving a crater. Their conclusion ranked erosion and cratering among the most serious threats the mission faces. Now scale it up. Take a grain weighing 1 milligram, a speck barely visible on a fingertip, and let it strike at 99% of light speed. The energy it delivers works out to somewhere around 130 tons of TNT, from something you would need a microscope to find. The obvious response is to detect these objects and steer around them. That option is not available, and the reason is beautifully, terribly simple. Your warning has to travel at the speed of light. So does the thing that is about to hit you. Send out a radar pulse. The pulse races ahead at light speed, strikes the object and returns. But while it makes that round trip, the object has been closing on you at 99% of that same speed. Run the arithmetic and the result is stark. Ping something that is 1 second away from hitting you, and the echo reaches you about 5 milliseconds before impact. 5,000ths of a second. A human blink takes roughly 40 times longer. At relativistic speed, detection and collision become effectively the same event. There is no early warning system possible, not because our sensors are poor, but because the messenger and the threat travel at nearly the same speed. You would learn about the obstacle from the crater it made. Each of these impacts creates something worse than itself. A high-energy particle stopping inside solid matter does not simply come to rest. It smashes into nuclei, which throw off fragments, which strike more nuclei. The Edelsteins note that incoming particles at these energies produce cascade showers, an avalanche of secondary particles generated inside the material. Your hull becomes a radiation source. The shield stops the arriving particle, then manufactures a spray of new ones aimed at everything behind it, like a single stone starting a landslide inside the wall meant to protect you, and every joule of all that absorbed energy has to go somewhere. Energy dumped into your hull becomes heat, and heat in a vacuum can only leave by radiating away as infrared light. The Edelsteins identify this explicitly. The mounting thermal load forces enormous expenditures of energy simply to keep the vessel cool. Radiate it fast enough, or cook. And then, at truly extreme speeds, something happens that no shielding strategy can address at all. Filling all of space is the oldest light in the universe, the afterglow of the Big Bang itself, released when the cosmos first became transparent. We call it the cosmic microwave background, and it has been cooling ever since. Today, it sits at about 2.7 degrees above absolute zero, around minus 270 degrees Celsius, roughly minus 455 Fahrenheit, the coldest, faintest, gentlest radiation in existence. Return to that sugar cube of space. Alongside its single hydrogen atom, it holds over 400 photons left over from the beginning of time. Harmless, ancient, everywhere, until you fly into them. In 2015, Ulvi Yurtseva and Stephen Wilkinson published an analysis of what those photons do to a ship at extreme Lorentz factors. Head-on motion blueshifts light, the same effect that raises the pitch of an approaching siren, applied to electromagnetic radiation. Fly fast enough into the microwave background, and those photons climb out of microwaves, through infrared, through visible light, through ultraviolet, into X-rays, and onward into gamma rays. They calculated the threshold precisely. When the blueshift factor reaches about 2.5 times 10 to the 8th, around 250 million, the incoming photons carry enough energy to strike a nucleus in your hull and convert into matter, an electron and a positron, created from a photon that began as the cold glow of the early universe. That corresponds to a Lorentz factor near 124 million, a speed of about 1 minus 3.3 times 10 to the minus 17, 17 nines after the decimal point. At that gamma, a single day aboard your ship would cost the outside universe roughly 340,000 years. And here is what makes it unanswerable. Every ordinary hazard so far arrives from outside, and can, in principle, be stopped by putting something in front of it. This one does not arrive. It is manufactured, inside whatever material you chose as protection, by photons that pass straight into it and turn into particles on the way through. Thicker shielding simply means more nuclei for those gamma rays to convert against. The relic light of creation, filling every cubic centimetre of the universe, becomes the thing that stops you. Step back and look at the shape of what we have found. Relativity says nothing about a maximum survivable speed. Mathematically, you may approach light speed as closely as your energy budget allows. But the universe is not the clean vacuum those equations assume. It is filled, thinly, invisibly but everywhere, with hydrogen, with dust, and with the fading light of its own beginning. And each of those becomes a weapon at a different point along the climb. Hydrogen turns lethal somewhere near half-light speed. Dust becomes explosive well below that. The background radiation ignites at Lorentz factors above 100 million. Nothing forbids the journey. Everything opposes it. There appears to be a practical speed limit written into the contents of space itself, sitting far, far below the theoretical one. And suppose somehow a future civilization solved every one of these problems. Suppose they built the shield, dissipated the heat, and survived the crossing. They would still face one final difficulty, and it is a strange one. At those speeds, the sky itself stops behaving the way any of us has ever seen it behave. The stars do not simply blur past. They gather, they change colour, and then, impossibly, they go out. So put a camera on the nose of the ship, aim it straight ahead at 99% of light speed, and look at the screen. Every film you have ever seen shows you the same thing at this moment. Stars stretching into long white streaks, rushing past the windows, flowing backward like rain on a windscreen. That image is wrong. Not slightly wrong. Wrong in almost every particular. The truth is stranger and considerably more disturbing. Two separate effects reshape the sky. They work at the same time, and neither one behaves the way intuition insists it should. Let's take them one at a time. The first effect has a name that sounds technical, and a cause you have already experienced with your own body. Aberration. Think of running through vertical rainfall. The rain is falling straight down, but the faster you run, the more it seems to slant in toward your face. And by the time you are sprinting, you are getting wet down the front of your shirt rather than on your head. The rain never changed direction. Your motion changed the angle at which it meets you. Light does exactly this. Move through it, and the direction it appears to come from shifts toward your line of travel. And we have known this for 3 centuries. In the 1720s, the English astronomer James Bradley pointed a telescope at a star called Gamma Draconis, hoping to detect the tiny wobble that would prove Earth orbits the Sun. He found a wobble, but the wrong one, at the wrong time of year. It took him years to understand what he had actually caught. Earth moves around the Sun at about 30 kilometers per second, roughly 19 miles every second. That motion tilts the apparent position of every star in the sky by a maximum of 20.5 arcseconds. An arcsecond means nothing on its own, so anchor it. 20.5 arcseconds is the width of a small coin viewed from about 200 meters away, the length of 2 football pitches. Tiny, utterly real, measured, published, and used to calculate the speed of light more than a century before Einstein was born. Now, increase Earth's speed by a factor of 10,000. At 99% of light speed, aberration stops being a delicate correction and becomes the dominant feature of your entire visual world. Every star shifts toward the direction you are traveling, not a little, enormously. Take the stars that ought to sit exactly beside you, 90 degrees off, out the side windows. At this speed, they appear about 8 degrees from dead ahead. Hold your fist up at arm's length. That fist covers roughly 10 degrees of sky. So half the stars in the universe, everything that should occupy the entire forward hemisphere around you, now crowds into a patch smaller than your fist, and stars that lie genuinely behind you swing forward too, pulled up over your shoulders and into the front of your view. You would be looking at objects you are flying away from. The sky does not streak past. The sky gathers. Everything falls forward into a shrinking circle, and the space around and behind that circle empties out. The nearest honest description is not a tunnel of streaking light. It is standing at the wrong end of a telescope, the entire cosmos crushed into a bright disk ahead, and darkness filling everything else. Push to 99.9%, and that forward hemisphere squeezes into about 2.5 degrees. 5 times the width of the full moon, and that is only the geometry. The colors have not even started yet. Everything ahead of you is approaching. Everything behind is receding. And approaching light shifts toward blue while receding light shifts toward red, the same principle that raises the pitch of a siren coming toward you and drops it as it passes. At 99% of light speed, that shift factor reaches about 14. So green starlight arriving from ahead, around 550 nanometers, the wavelength your eye is most sensitive to, arrives compressed to roughly 39 nanometers. That is not violet. That is extreme ultraviolet, bordering on X-rays. Your retina has no receptor for it whatsoever. Behind you, the same green light stretches out to about 7.8 microns. Deep infrared, also invisible. And here is a detail that catches almost everyone out. You might assume the dividing line, the boundary between blue-shifted and red-shifted sky, sits neatly at 90 degrees, straight out the side. It does not. Because your own clock runs slow relative to the outside universe, even light arriving from directly sideways reaches you reddened. The boundary between blue and red lies ahead of you, and the faster you travel, the further forward it slides. The blue region shrinks as you accelerate. It does not grow. This is where a beautiful idea entered the culture and refused to leave. The German rocket engineer Eugen Sanger worked through the color shifts and pictured a ring. Stars ahead shifted through violet, stars behind through red, and a band of ordinary visible color circling between them like a rainbow around the direction of flight. In 1972, the science fiction writer Frederik Pohl encountered the concept and gave it a name that stuck forever. His novella, The Gold at the Starbow's End, described a crew watching a full-circle rainbow ahead of their ship. The Starbow. It has appeared in countless illustrations ever since. Then, in 1979, John McKinley and Paul Doherty at Oakland University in Michigan actually ran the calculation properly. They published it in the American Journal of Physics. Sanger's version had treated every star as a single, pure yellow point of light. McKinley and Doherty instead modelled the real sky, real stars, at their real temperatures, each radiating a full spectrum rather than one colour. Then they added a third relativistic effect that earlier treatments had left out, the transformation of intensity, which McKinley called the headlight effect. Finally, they folded all of it through the actual response curve of the human eye. Their conclusion appears in the paper's own abstract, and it is blunt. A starbow does not appear. Instead of a tidy spectral ring, their computer-generated images showed something messier and far less friendly. A crowded, distorted forward field, and expanding dark regions, one growing around the star you left, another around the star you are heading toward. The most famous image of relativistic travel turns out to be an artifact of an oversimplified model. Researchers have continued refining the picture since, and the details are still being worked over. But the poetry did not survive contact with the physics. Push harder, and something happens that no film has ever attempted to show. The stars ahead do not become brilliant. They do not turn blue-white and blaze. They disappear. Their light climbs past violet, out of the visible band entirely, into ultraviolet and then X-rays. Your eyes have no more access to it than they have to a radio broadcast. The star is still there. It is still pouring energy at you. You simply cannot see any of it. Behind you, the same thing happens in the opposite direction. Starlight stretches through infrared and onward into microwaves and radio. That sky darkens too. For a while, a band of ordinary visible stars survives somewhere in between, the narrowing region where the shift happens to be modest. But as you climb, that band thins, slides forward, and finally closes. Then the visible universe switches off, not dimmed, not blurred, gone in both directions at once, because every photon that reaches you has been shifted out of the narrow octave of wavelengths your species evolved to detect. And yet the forward view would not be black. Something else moves into the gap. Filling all of space is that ancient background radiation, the relic glow of the early universe, arriving from every direction with a wavelength of about 1 millimeter, roughly the thickness of a credit card. Ordinarily, no eye can perceive it. Its wavelength sits far outside the visible range, in the microwave band, but blueshift it hard enough, and it climbs, somewhere around a Lorentz factor of 1,000, where a single year aboard your ship costs the outside universe about 1,000 years. That millimeter-scale radiation compresses into visible light. Sit with the strangeness of that image for a moment. Every star has vanished, the constellations are gone, the Milky Way is gone, and directly ahead of your ship, concentrated by aberration into a small bright circle, glows the oldest light in existence, the afterglow of the universe's own beginning, made visible for the first and only time by the speed of your ship. Not stars, not galaxies. The Big Bang itself as a lamp in the darkness ahead. It would be the last thing anyone ever saw, because the climb does not stop there. Keep accelerating, and that visible glow shifts onward, through violet, into ultraviolet, into X-rays, eventually into gamma rays. The final light in your sky follows every other light out of the visible range, and the forward view goes dark again, this time permanently. Meanwhile, the other half of the picture completes itself. The headlight effect that McKinley identified concentrates radiation intensity toward the direction of travel. Whatever energy exists in your surroundings pours forward, into that shrinking circle, while the view behind you fades toward nothing at all. A cone of invisible fire ahead, emptiness astern, The few objects that did pass close enough to resolve would not look flattened, whatever the textbooks used to claim. They would appear turned, the rotation that Terrell and Penrose predicted, and that a Vienna laboratory finally photographed. And clocks would misbehave in a way that seems, at first glance, to contradict everything about slowing time. A clock ahead of you, one you are rushing toward, would visually appear to run roughly 14 times fast at this speed. A clock behind you would appear to crawl at a 14th of its normal rate. The universe would look as though it were fast forwarding in front of you and freezing behind you. Hold that against what you already know, because the tension is real and worth resolving. Time dilation is a genuine physical effect. Moving clocks really do run slow, and the traveller really does come home younger. What you would see through a telescope is something different. The arrival rate of light signals, compressed by your approach and stretched by your retreat. One is the underlying physics. The other is the messenger service delivering the news. Both are true. Only one of them changes who ages. Now step outside the ship and consider how it would appear to someone else. Optically, it would be almost nothing. Any light it emitted forward would be shifted clean out of the visible band before it reached a distant observer. But in gamma rays, it would be extraordinary. Ulvi Yurtsever and Stephen Wilkinson, working at Raytheon in California, published exactly this analysis in 2015. Their conclusion carried a striking implication. A spacecraft traveling close to light speed would generate a distinctive high-energy signature, one they argued should be detectable with technology we already possess, which turns this entire problem inside out. If any civilization anywhere has ever built a relativistic vessel, it may not need to announce itself. The physics of moving fast would announce it, a moving point of hard radiation, crossing between stars, obeying laws we already understand. Researchers have proposed searching for precisely that. Not radio messages, exhaust trails. We may be looking for the wrong signal entirely. And now the practical consequence, which is arguably the worst of all. Every spacecraft humanity has ever flown navigates using a star tracker. The principle is simple and beautiful. A small camera photographs a patch of sky, compares the pattern to a catalogue stored on board, and works out precisely which way the vehicle is pointing. Voyager uses one. Every planetary probe uses one. It is the most reliable orientation instrument we have ever built. Now hand that instrument the sky we have just described. The star patterns are gone, crushed forward, shifted out of the visible band, and rearranged into a configuration matching nothing in any catalogue ever compiled. The camera would photograph an empty frame with a bright smear ahead and find no match anywhere in its memory. Your ship would be moving faster than anything in history, through a medium that behaves like reactor radiation, unable to see obstacles before they arrive, and now unable to determine which way it is facing. You would be flying blind, not metaphorically, optically, navigationally, completely blind, in a vessel where a single microscopic grain could destroy you, at a speed where nothing about the universe looks the way it does from here, and you would have chosen this, deliberately. So that is the full picture. Time stretches, space folds, the energy bill runs to infinity, the vacuum turns lethal, and the sky itself simply switches off. Every one of those consequences follows from a single stubborn fact, that light speed refuses to change, no matter who is measuring it. We have spent this whole climb treating relativistic travel as a distant engineering fantasy, something a future civilization might attempt with resources we cannot imagine. But here is what should genuinely unsettle you. Nature is doing all of this, right now, without a ship, without an engine, without any effort at all. Particles are crossing the galaxy at speeds that make 99% look sluggish. Some of them are passing through your body as you listen to this, and a few of them carry energy so absurd that, when we first detected one, physicists genuinely questioned whether the instruments had malfunctioned. They had not. Wherever you are right now, sitting, lying down, holding a phone or a mug, Hold out one open hand for a moment and look at your palm. Roughly 100 subatomic particles are passing through it every minute, almost 2 every second. They enter through the back of your hand, cross your bones and blood without noticing them, exit through your palm, and continue down into the ground beneath you. They are called muons, heavier cousins of the electron produced about 15 kilometers, 9 miles, above your head, when cosmic rays from deep space smash into the top of the atmosphere. At sea level, physicists measure their arrival rate at roughly 1 muon per square centimeter per minute. Your palm covers about 100 of those squares. The rate has been measured, cross-checked and relied upon for decades, and it does not stop. Not at night, not indoors, not underground until you go very deep indeed, and every single one of them is a demonstration of relativity and progress. Muons are unstable and short-lived. At the speeds they travel, an average muon should decay after covering only a few hundred meters, a distance you could walk in 5 minutes. They are born 9 miles up. By any ordinary reckoning, almost none of them should ever reach the ground. They arrive anyway, in enormous numbers, because their clocks are running slow. Their typical energies put their Lorentz factor somewhere near 40, and that stretched lifetime is exactly what carries them down through the atmosphere and into your hand. You are not reading about an experiment, you are standing inside one continuously for your entire life. But muons are the gentle end of this. Look further out, and the universe builds machines that make our finest engineering look like a child's toy. On the night of the 15th of October, 1991, at Dugway Proving Ground in the Utah desert, an instrument called the Fly's Eye was staring at the sky. The Fly's Eye was a field of 67 mirrors watching for a specific faint signature, the ghostly ultraviolet glow that nitrogen molecules give off when an incoming particle detonates into a cascade of secondary particles miles overhead. That night, it caught something the team initially struggled to believe. A single subatomic particle. One, carrying an energy of about 3.2 times 10 to the 20th electron volts. Numbers that large mean nothing until you convert them, so here is the conversion. That single particle carried roughly 51 joules of energy. 51 joules is the energy of a brick dropped onto your foot from waist height, or, as physicists more commonly put it, a baseball thrown at about 95 kilometers per hour, around 60 miles per hour. A baseball contains something like 10,000 million atoms. This was one particle. The team named it the Oh My God particle. More than 3 decades later, it remains the highest energy cosmic ray ever observed. To carry that much energy, it had to be moving at a speed that is difficult to write down and almost impossible to feel. 99.99% of light speed, with 21 nines running past the decimal point before any digit finally changes. Try to picture what a number that extreme actually buys you. Line the particle up beside a photon of light and start a race lasting 1 full year. Over that year, both travel roughly 9.5 million kilometers. At the finish, the particle is behind by about 46 nanometers, less than 1,000th of the width of a single human hair. After a year, if the particle was a proton, as most analyses assume, its Lorentz factor was somewhere above 300,000 million, which means 1 second of its own experience corresponds to something close to 11,000 years of ours. Turn that around, and it becomes genuinely staggering. From inside that particle's frame, the entire Milky Way, 100,000 light-years of stars, would be crossed in about 9 seconds. 9 seconds. For a journey that light needs 1,000 centuries to complete. For comparison, the protons we accelerate in the Large Hadron Collider, using a 27-kilometer machine and decades of engineering, carry roughly 40 million times less energy than that single particle did. Nobody could explain it, and for years many quietly wondered whether the measurement had simply been wrong. Then, on the 27th of May, 2021, it happened again. Out in Utah's West Desert near the town of Delta, 507 detector stations sit in a grid covering 700 square kilometers, about 270 square miles. Most nights, they record nothing remarkable. That night, 23 of them fired at once, in a splash spreading across 48 square kilometers of desert. The telescope array collaboration, led by the University of Utah and the University of Tokyo, published their analysis in the journal Science in November of 2023. The particle's energy came out at 2.4 times 10 to the 20th electron volts, the second highest ever recorded, and again equivalent to a brick landing on your foot. They named it the Amaterasu particle, after the sun goddess of Japanese mythology. 2 different instruments, 2 different detection techniques, 30 years apart. Whatever these things are, they are real, and then the researchers traced where it came from. The arrival direction pointed back toward the local void, an enormous, nearly empty region of space bordering our own galaxy, a place with no obvious candidate for producing anything at all, let alone the most violent particle acceleration known. As John Bells, one of the study's co-authors, put it, the events appear to come from completely different places in the sky. No single mysterious source explains them. Whether the local void is truly the origin remains actively debated. Magnetic fields along the way can bend even these particles slightly, and some researchers argue the real source may be a nearby starburst galaxy instead. That question is still open. Here is the part that turns a puzzle into a genuine crisis. These particles should not have been able to reach us at all. In 1966, working independently, Kenneth Greisen in the United States and Georgy Zatsepin and Vadim Kuzmin in the Soviet Union realized something about protons crossing intergalactic space. A proton moving fast enough sees the ancient background radiation of the universe the way a relativistic ship would, compressed, hardened, transformed into something far more energetic than the microwaves we measure from Earth. Above a threshold energy of about 5 times 10 to the 19th electron volts, roughly 8 joules, a brisk tennis serve packed into one particle, those collisions stop being harmless. The proton and the photon collide hard enough to manufacture new particles called pions. Each collision bleeds away energy, and the process repeats over and over until the proton drops below the threshold. The distance over which this drains a proton dry works out to roughly 160 million light-years. To feel that distance, consider what light leaving a source that far away was passing when it set out. Earth was in the middle of the Jurassic. Dinosaurs walking, the first birds not yet fully formed. So any proton arriving here above that threshold must have been produced somewhere inside that bubble. Anything from further away should have been ground down long ago. Both the Oh My God and Amaterasu particles sailed straight past that limit, and nothing inside that bubble in the direction they came from looks remotely capable of producing them. The universe imposes a speed limit on protons crossing intergalactic space. Something appears to be ignoring it. Physicists have proposed several ways out, and none has won. The first says the source is simply nearby, some object within that 160 million light-year bubble that we have not identified, perhaps hidden or no longer active. The second says the particles are not protons at all, but heavier atomic nuclei. Iron, perhaps. Heavier nuclei behave differently against the background radiation, and their arrival directions bend more in magnetic fields, which would scramble any attempt to trace them home. The third is the most radical. Some theorists have suggested the calculation itself may fail at these energies, that Lorentz invariance, the deep symmetry underlying all of special relativity, might break down in the extreme. If it did, the pion production process would not proceed as predicted, and the particles could cross the universe untouched. The telescope array team themselves wrote that these events might follow particle physics unknown to science. Sit with that for a moment. The most extreme motion we have ever observed may be pointing at a gap in the theory that explains motion itself. The observations do not agree with each other either, and this tension has not been resolved. In the northern sky, the telescope array has reported a concentration of the highest energy events, a region roughly 20 degrees across, near the constellation Ursa Major. In one analysis, 19 of 72 ultra-high energy events came from that patch, which covers only about 6% of the sky. Random chance predicts about 4.5%. They call it the hot spot, and it does not sit where anyone expected, not on the active galactic nuclei that were the favourite suspects. Meanwhile, in Argentina, the Pierre Auger Observatory watches the southern sky across roughly 3,000 square kilometres, more than 4 times the telescope array's area. Auger has detected something different, a large-scale dipole, a gentle lopsidedness in arrival directions above 8 exaelectron volts, now measured with very high statistical confidence. That dipole points away from our own galaxy, arguing strongly that these particles come from outside it. But Auger sees no strong equivalent of the hotspot, and the two experiments' energy spectra diverge at the very highest energies, despite agreeing closely below. A joint working group from both collaborations is trying to reconcile them. Recent proposals suggest a single bright nearby source could explain the discrepancies at once. Nothing is settled. 2 of the finest instruments ever built are looking at the same universe and reporting different skies. For the machinery that might do this, the leading suspects are the largest engines in existence. 5 billion light-years away, in the constellation Virgo, sits a quasar called 3C279. Its light left before the Sun and Earth had finished forming. At its centre lies a black hole of roughly 1,000 million solar masses, about 250 times heavier than the one at the centre of our own galaxy. Matter spiralling into it powers 2 jets of plasma, fired out in opposite directions at velocities close to light speed. One of those jets happens to point almost directly at us, within about 2 degrees of our line of sight. 2 degrees is roughly 4 times the width of the full moon, and when astronomers tracked the bright knots inside that jet across years of observation, they measured something that should be impossible. The knots appear to move at up to 20 times the speed of light, except they do not. And understanding why is one of the most elegant pieces of reasoning in astrophysics. Picture material moving at almost light speed, aimed nearly straight at you. It emits a flash of light, then it travels forward and, a little later, emits another. But in the time between those 2 flashes, the material has closed much of the distance the first flash had to cover. The second flash, therefore, has a far shorter journey to make. It arrives hard on the heels of the first, compressed in time. The jet is chasing its own light, and because you receive the signals bunched together, the sideways motion between them looks enormously faster than it truly is. Measure it properly, accounting for the geometry, and the real speed of that jet in 3C279 comes out at about 99.7% of light speed, blisteringly fast, comfortably below the limit. The same illusion appears in the jet from M87, the galaxy whose black hole gave us the first direct image of an event horizon. It appears everywhere astronomers have looked carefully, and in every single case examined, the answer is the same. The apparent violation dissolves. The real velocity sits below c. Einstein's wall holds. Nature reaches astonishingly close. Nature never touches it. So look at what we have gathered. Particles crossing the galaxy in 9 seconds of their own time. Jets that fake superluminal motion so convincingly that it took astronomers years to unpick. A background radiation that should bleed the fastest protons dry, and evidently sometimes does not. The universe has been running relativistic experiments at scales we cannot approach continuously for 13.8 thousand million years. It has produced energies 40 million times beyond our best machines. It has come within a hair's breadth of the barrier, closer than we will ever manage, and it has never once crossed it, not in a quasar jet, not in a cosmic ray, not in any observation ever made, anywhere, by anyone. Which brings us finally to the question that every curious person arrives at eventually, the one that no amount of engineering pessimism ever quite silences. The wall holds against everything we have. Fine. But what actually happens on the other side of it? The question deserves a more careful answer than most people give it, because relativity's actual prohibition is narrower and stranger than the popular version. Special relativity does not forbid faster-than-light objects. Read that again, because it surprises nearly everyone. What relativity forbids is crossing the barrier, taking something that moves slower than light and accelerating it up through the wall. That is the journey that costs infinite energy, but an object that was never on this side to begin with. The mathematics has no objection to it at all. Einstein himself was careful about this. In his 1905 paper, he noted only that for velocities greater than light, the reasoning becomes meaningless. He restricted the band to things being accelerated up from below, so physicists went looking for what might already be over there. In 1962, Oleksandr Myron-Bilaniuk, Vijay Deshpande, and George Sudarshan sketched how such particles could exist without contradicting relativity, provided they had been superluminal from the instant of their creation. 5 years later, Gerald Feinberg at Columbia University developed the idea into a full quantum field theory and gave it the name that stuck. He called them tachyons, from the Greek tachys, meaning swift. He had taken the inspiration in part from a science fiction story, and tachyons would behave in a way that inverts everything your intuition knows about motion. For ordinary matter, adding energy adds speed. Push harder, go faster. A tachyon does the opposite. Drain energy from a tachyon and it accelerates. Give it energy and it slows down. Take all the energy out and it moves infinitely fast. Try to slow it all the way down to light speed, and you would need infinite energy to do it. Picture a mirror image of our own predicament. We are trapped below the wall, unable to climb up to it. A tachyon would be trapped above the wall, unable to fall down to it. The same barrier, seen from the other side, equally impassable, and nobody has ever found one. Physicists have looked seriously and repeatedly since the 1960s, in accelerators, in cosmic ray detectors, in astrophysical observations. Interest peaked in the late 70s, when dozens of papers a year carried the word in their titles. Every experimental search came back empty. Something interesting happened to the idea in the decades since. The word survived. The particle did not. In modern quantum field theory, physicists still say tachyon constantly, but it no longer means a faster-than-light object. When a field is described as tachyonic today, it signals something quite different, that the theory is sitting in an unstable configuration, like a pencil balanced on its point, waiting to topple into a lower energy state. The physicist Lisa Randall has put the shift plainly. A tachyon, in current understanding, marks an instability inside a theory, not a real particle appearing anywhere in nature. The mathematics that once looked like a doorway turned out to be a warning light. But suppose one existed anyway. Suppose you could build a transmitter that sent signals faster than light. The trouble that follows has almost nothing to do with velocity. Recall that observers moving at different speeds genuinely disagree about which distant events happen at the same moment. That disagreement is real, measured, and unavoidable. Now push a signal faster than light through that geometry, and something breaks. For observers in some reference frames, the signal arrives before it was sent, not appears to. Does. Their measurement of the departure time comes after their measurement of the arrival time, and their frame is every bit as valid as yours. Richard Tolman spotted this consequence as early as 1917, and in 1970 Gregory Benford, David Book, and William Newcomb worked the logic through to its conclusion in a paper with a name that is hard to forget: the tachyonic anti-telephone. Here is how it works. You send a superluminal message to a friend moving away from you at high speed. In your frame, it takes a moment to arrive. Your friend receives it and immediately fires a superluminal reply back, but from their frame of motion, aimed at the version of you that existed earlier. Chain the two together, and the reply lands before you sent the original. You could receive the answer to a question you have not yet asked. You could learn a result before the experiment. You could send yourself a warning about an accident, then avoid it, so the accident never happened, so the warning was never sent. That is not a paradox about going fast. Any genuine faster-than-light signal is, automatically and unavoidably, a machine for talking to the past. Cause and effect stop being separate categories, and nothing in physics survives that, which is exactly why the world reacted the way it did in September of 2011. Beneath the Alps, a beam of neutrinos leaves CERN in Geneva and travels straight through solid rock for 730 kilometers, about 454 miles, to a detector buried under a mountain in central Italy. Neutrinos barely interact with matter, so the crust of the Earth is no obstacle at all. The experiment was called OPERA, and on the 23rd of September, at a seminar at CERN, the collaboration announced a result they could not explain. The neutrinos were arriving about 60 nanoseconds early, 60 billionths of a second. Light travels roughly 18 meters in that time, about the length of a bowling lane, from the foul line to the head pin. Against a journey of 730 kilometers, that gap is almost nothing, but it was measured at 6 sigma, and it meant the neutrinos had beaten light. Notice what the collaboration did next, because this is science working properly. Of roughly 160 members, about 15, mostly senior researchers, declined to put their names on the preprint. They wanted more checks first. The team published anyway, explicitly inviting the world to find their mistake. Physics held its breath for months. Hundreds of papers appeared attempting to explain, reanalyze, or demolish the result. Then, in November, a neighboring experiment at the same laboratory pointed out that superluminal neutrinos should have shed a telltale form of radiation along the way. No such radiation appeared, and in February of 2012, OPERA found the fault. 2 of them. A fiber optic cable carrying the timing signal from a GPS receiver to the master clock had not been screwed in properly. That single loose connector shifted the measurement by about 73 nanoseconds, in exactly the direction that would make neutrinos look fast. A second problem, an oscillator running outside its specification, pushed slightly the other way. Photographs later showed the cable had been sitting loose since at least the previous October. Corrected, the neutrinos traveled at a speed entirely consistent with light. Relativity survived, untouched. The most famous challenge to Einstein in a generation came down to a cable that was not tightened. Special relativity then holds. But general relativity, Einstein's later theory, the one describing gravity as curved space-time, leaves a gap that has never been closed. Space itself has no speed limit. Nothing may move through space faster than light. But space can expand, and expansion carries no such restriction. This is not speculation. Right now, beyond a distance of roughly 14,000 million light-years, galaxies are receding from us faster than light, purely because the space between us keeps growing. No law is violated. Those galaxies are not moving through anything. The road between us is being lengthened. So, a question naturally follows. Could you do that deliberately? Could you make space do the traveling for you? In 1994, a Mexican physicist named Miguel Alcubierre published a short paper in Classical and Quantum Gravity that has echoed ever since. He described a geometry, a solution to Einstein's equations, in which space contracts in front of a small region and expands behind it. Inside that region, space-time stays flat and ordinary. A ship sitting there feels no acceleration, experiences no time dilation, and never moves through the space around it at all. The bubble carries it, like standing on a moving walkway rather than running. And because the ship never travels faster than light locally, special relativity never gets violated. On paper, the arrangement permits arbitrarily fast crossings between stars. Then the bill arrived. Making space behave that way requires a very specific kind of material, one with negative energy density, matter that gravitationally pushes instead of pulling. Nothing in the known universe supplies it in bulk. In 1997, Michael Fenning and Larry Ford at Tufts University applied quantum inequalities to Alcubierre's geometry, mathematical limits on how much negative energy quantum theory permits, and for how long. Their paper's title states the verdict: the unphysical nature of warp drive. Their analysis showed the wall of the bubble would have to be extraordinarily thin, on the order of a few hundred Planck lengths. A Planck length is around 100,000 millionth of a meter. Put differently, A single proton is roughly 50 million times wider, so the bubble wall would need to be thinner than anything that could be constructed from any known form of matter, and squeezing the required negative energy into a shell that thin drives the totals to values with no physical meaning. A year later, Ken Olam sharpened the general point in Physical Review letters. Superluminal travel, he argued, requires negative energies, not as a quirk of Alcubierre's particular design, as a structural requirement. And yet, the field did not die. Over the past few years, it has become genuinely active again, and the results are more interesting than either the enthusiasts or the skeptics expected. In 2021, Alexei Bobrik and Gianni Martire published a paper reframing the whole problem. Any warp drive, they showed, including Alcubierre's, amounts to a shell of material moving inertially at some velocity, which means every warp drive still needs conventional propulsion to get going. But they also demonstrated something encouraging. A whole class of subluminal warp bubbles can, at least in principle, be built from ordinary positive energy. They also cut Alcubierre's negative energy requirement by a factor of about 100. That same year, Eric Lentz proposed superluminal soliton solutions he argued could be sourced by positive energy plasma. Sean Fell and Lavinia Heisenberg published related positive energy work. Lentz's superluminal claim remains contested. Other groups have since published analyses arguing that his solutions do, in fact, violate the energy conditions after all. That disagreement has not been settled in the literature. Then, in 2024, a team led by Jared Fuchs at Applied Physics, working with researchers at the University of Alabama in Huntsville, published something remarkable: a constant velocity warp drive solution that satisfies all of general relativity's energy conditions. No exotic matter. Their design works rather like a conveyor belt. Large quantities of perfectly ordinary energy circulating rapidly around the passenger volume, dragging the interior along with it. Passengers would feel no acceleration. The physics is clean. And it is subluminal. Look carefully at the pattern across 3 decades of work. Every solution that becomes physically reasonable stops short of the light barrier. Every solution that crosses it demands matter nobody has found. Even setting the energy aside, superluminal bubbles carry a defect that may be fatal on its own. A bubble traveling faster than light generates horizons, surfaces beyond which signals cannot pass, and the pilot sits behind one of them. Nothing the ship emits can reach the front of its own bubble, which means the bubble cannot be steered, adjusted, or switched off from inside. The geometry would have to be laid down in advance, along the entire route, by something already able to travel it. Critics have a blunt name for this: you need one to build one. Sergei Krasnikov proposed a partial answer in 1998, a permanent tube of modified space-time, built on the outbound trip at ordinary speeds, allowing rapid return journeys afterward. Alan Everett and Thomas Roman analysed it the previous year and found it running into the same exotic matter requirement. Nobody has solved this. Suppose all of it fell into place. Suppose the energy conditions were satisfied and the horizons engineered away. In 1996, Alan Everett published a short paper in Physical Review D with a devastating title, Warp Drive and Causality. He showed that an Alcubierre drive, once genuinely superluminal, can be used to construct closed time-like curves, loops in space-time, paths that return to their own past. The anti-telephone again, arriving by a different road entirely. Any true faster-than-light capability, tachyon, warp bubble, wormhole, anything, brings time travel with it as an inseparable consequence. In July of 1992, Stephen Hawking published a paper in Physical Review D proposing that the universe simply refuses to allow this. His argument was technical, but the intuition is graspable. As a space-time approaches the moment a time loop would close, quantum vacuum fluctuations, the restless, unavoidable jitter of empty space, begins circulating around the forming loop. Each pass amplifies them. The calculated energy density diverges, and the geometry tears itself apart before the loop can complete. Hawking called it chronology protection. He also offered a piece of observational evidence that is difficult to argue with. We have never been visited, as he put it, by hordes of tourists from the future. But the conjecture is a conjecture, not a theorem. Other physicists, including Li Xin and colleagues, have published cases in which the relevant quantities stay finite, where the horizon might survive the fluctuations after all. As one survey of the field puts it, no consensus currently exists on whether the instability is genuine. The honest position is this: settling it almost certainly requires a working theory of quantum gravity, a unification of Einstein's gravity with quantum mechanics that physics does not yet possess. We cannot prove the door is locked. We only know that nothing has ever come through it. Every other route runs into the same wall. Traversable wormholes, tunnels connecting distant regions, require exotic matter to hold their throats open. The Casimir effect, where two closely spaced conducting plates produce a genuine negative energy density between them, remains the only laboratory source we have, and the quantities involved are almost unimaginably small. Krasnikov tubes, exotic matter, and quantum entanglement, the effect where measuring one particle instantly determines the state of its distant partner, closes the final door itself. The correlations are real and experimentally confirmed, but the no communication theorem proves that no information can be transmitted through them. The results look random at each end until the two are compared, and that comparison must travel at light speed like everything else. Nature seems to have anticipated every workaround. So the barrier holds, not as an engineering obstacle, but as the load-bearing structure of a universe in which effects follow their causes, which leaves exactly one road to the stars, the slow one, below the wall, paid for in time. And the price of that road is not measured in fuel or energy or radiation. It is measured in everything you leave behind. To understand what that price actually is, we have to go back to the oldest and most misunderstood consequence in all of relativity. Two twins, same age, same day of birth. One boards a ship and flies to a star 10 light-years away at 99% of light speed, then turns around and comes home. The other stays on Earth and waits. Run the numbers and the outcome is unambiguous. On Earth, a little over 20 years pass. Aboard the ship, not quite 3. The travelling twin steps off at the age of 33. The twin who waited is 50. And here is where almost everyone gets stuck. If motion is relative, if there is no absolute frame, no privileged place to stand, then the situation ought to be perfectly symmetrical. From the ship's frame, Earth was the thing that raced away and came back. From Earth's frame, the ship did. Each twin, watching the other through a telescope, genuinely sees the other's clock running slow. So how can they possibly disagree about who ended up older? Both cannot be right, and yet neither seems to have any better claim than the other. The puzzle troubled physicists for years. Some very good ones got it wrong. The resolution is beautifully simple, and it hinges on one thing. The situation is not symmetrical. It only looks that way. The twin on Earth stays in a single, unchanging frame of reference for the entire trip. The traveller does not. At the halfway point, the ship must slow, stop, reverse, and accelerate home. That turn changes everything, because it is not a matter of bookkeeping. It is physically felt. Think about sitting in a car. Cruising at a steady speed on a smooth road, you feel nothing at all. Close your eyes and you cannot tell whether you are moving or parked. That is the whole point of relativity. But the moment the driver brakes hard and swings the wheel, your body knows. You are pressed into the seatbelt, thrown against the door. No one on board has to be told a turn happened. The travelling twin experiences exactly that. Crushing acceleration, felt in the bones, for as long as the turnaround lasts. The twin on Earth feels nothing whatsoever. Only one of them changed frames. Only one of them can point to a moment when their entire notion of now swung across the sky. And that asymmetry is what breaks the tie. The traveller comes home younger, not as a trick of perspective, not as an illusion produced by signal delays, as a physical fact that would show on both their faces. We have watched smaller versions of this happen for over 50 years, in atomic clocks carried on aircraft, in particles held in storage rings, in satellites that must be corrected daily or fail. The effect is not disputed by anyone. Only its scale has ever been in question. So take the physics we have been climbing through and apply it to a real voyage. Build a ship that accelerates at 1G, the same gentle pull you feel standing in your kitchen, which conveniently gives the crew ordinary weight for the entire journey. Accelerate for the first half of the trip, turn over, decelerate for the second half. Do the same coming back. Now watch what a career aboard that ship buys you. 10 years of your life, out and back, carries you about 11 light years. 26 years pass at home. Difficult, but survivable. You return to friends who have aged more than you, to a world you still recognize. Give it 20 years of your life. You reach roughly 170 light years. On Earth, about 345 years have gone by. You left in a world of steam and arrive in one you cannot imagine. 30 years aboard reaches around 2,200 light years, and 4,500 years on Earth. Leave now, and you return to a future as far ahead of today as the building of the Great Pyramid is behind it. And then the curve does what curves do in this story. 40 years aboard that ship, a single working life from your 20s to your 60s, takes you to the center of our galaxy and back. 30,000 light years out, 30,000 back. You would see the crowded core of the Milky Way with your own eyes. You would return with data no human being has ever possessed. And roughly 60,000 years would have passed on Earth. Reach for something to hold that against. 60,000 years ago, our own species was still spreading out of Africa. Neanderthals were living in Europe. Nothing that could be called a city, a written word, or a nation existed anywhere on the planet. That is the size of the gap you would step across, in one direction, in 40 years. Push to 50 years aboard, and the Earth clock runs to something near 780,000 years, a stretch of time longer than our species has existed. Homo sapiens is only about 300,000 years old. So the honest description of relativistic travel is not exploration, it is emigration. One way, permanent, and irreversible. Consider what actually waits for you when the ramp comes down. Everyone you knew is gone, not recently, but geologically. Their descendants are gone. The nations that funded your mission are gone, along with the languages those nations spoke. Your own speech would be archaeological, a curiosity for specialists, if any specialist happened to still be interested. The mission itself has almost certainly been forgotten. 60,000 years is long enough for the memory of a launch to fade from history entirely, then be rediscovered, then be doubted, then be forgotten again. You would carry knowledge no one asked for, on behalf of a civilization that no longer exists, for the benefit of people who never heard of you, and you would have watched the conversation die on the way out. Radio contact does not fail suddenly. It degrades, message by message, in a way that is quietly one of the saddest consequences in this whole story. Early in the voyage, you send a message, and a reply comes back in weeks, then months, then years, because every message must cross a gap that keeps growing at very nearly light speed in both directions, then decades between question and answer. Somewhere along that curve, the correspondence stops being a conversation and becomes something else. You are no longer speaking with people. You are speaking with an institution, then with a tradition, then with a legend. And eventually the replies simply stop, not because anyone chose to stop answering, because no one is left who was waiting. The last transmission you ever receive would be sent by someone who was born long after you departed, and who would be long dead before their words reached you. Extend that to a species rather than a ship, and the consequences turn strange. Imagine a civilization that genuinely mastered relativistic flight, that scattered vessels across the galaxy at high fractions of light speed. What would it actually be? Not an empire, not a federation, nothing that could hold a meeting, agree a law, or fight a war. Every ship would be running on its own clock, at its own rate, in its own private stream of time. Two crews leaving the same port on the same day at slightly different speeds would return to find centuries between them. The concept of a shared present moment, the thing that lets any society exist at all, would dissolve. Such a civilization would not expand. It would fracture into isolated timelines that can never be resynchronized. Some researchers have suggested this as one consideration among many when we ask why the sky is silent, that the physics of interstellar distance may make coordinated galactic civilizations essentially impossible, whatever anyone's technology. Nobody can currently test that idea, and it remains one proposal among many for the Fermi question. But it does follow from physics we are confident about. There is a final consequence, and it is the one that keeps some researchers awake. Any ship capable of relativistic flight is automatically a weapon. Take a modest vessel, 1,000 tons, roughly the mass of a small naval ship, and give it 99% of light speed. The kinetic energy it carries works out to somewhere above 5 times 10 to the 23rd joules. For comparison, the asteroid that struck the Yucatan 66 million years ago and ended the age of dinosaurs released energy, estimated in that same range, around 100 million megatons. A relativistic starship does not need a warhead. It is the warhead. Its ordinary cruising energy is extinction scale, and no defense is possible because, as we have seen, nothing would detect it in time. There is no known way to make relativistic travel safe, or cheap, or reversible. Now step back and look at everything we have climbed through. Time that stretches without limit, distance that folds, an energy bill that runs to infinity, a vacuum that turns lethal, a sky that goes dark, a barrier that no theory, no metric, and no exotic geometry has ever credibly crossed. Read as a list, that sounds like a universe designed to keep us in, but that reading has it exactly backwards. The speed of light is not a fence someone erected across our path. It is not an obstacle, a limitation, or a piece of cosmic bad luck. It is the reason anything happens in any order at all. Every superluminal route we examined collapsed for the same reason, not because it was too fast, but because it let effects arrive before their causes. Take the barrier away, and you do not get a universe with faster travel in it. You get a universe where the past is reachable, where answers precede questions, where nothing can be said to have caused anything else. You get no history, no memory, no decisions, no before and no after. The wall that traps us is the same wall that makes a coherent universe possible. It is not the bars on the window, it is the frame that holds the house up. So return to where all of this began. What happens as you approach the speed of light? Time stretches until a day aboard costs a lifetime outside. Distance folds until a galaxy fits inside a neighborhood. The emptiest space in existence ignites into radiation, and every star in the sky slides out of view until the only light left ahead of you is the glow of the beginning itself. But none of that is the real answer. Approaching light speed does not free you from the universe. It reveals what the universe has been the whole time. Space and time are not a stage that events happen on. They are not a fixed backdrop, indifferent to what moves across them. They are moving parts, bending, stretching, trading against one another, inside a single structure that has been holding together since the first moment. We only fail to notice because we live so slowly. Here is the part that stays with you, I think. Once you have followed the whole climb, you are already traveling, not metaphorically. Every one of us is moving through space-time right now, at the only rate our bodies permit, 1 second per second, straight forward through time, spending nothing on motion through space. That is one extreme of the same structure, all time and almost no distance. Light chose the other extreme, all motion and no time at all. Physicists are careful here, and the caution matters. Light has no valid frame of reference, so strictly speaking, it has no point of view we can borrow. But the mathematics is unambiguous about one thing. The proper time elapsed along a beam of light's path is exactly 0. Between those two limits, our slow forward crawl and light's timeless sprint, lies every possible motion, every journey ever made, everything that has happened, and everything that ever will. The wall we spent all this time trying to break is the thing that gives that range its shape. So look up tonight, if the sky is clear. The light landing on your eye from the faintest star up there has been crossing the dark for centuries or thousands of years or longer. Along the way, it has been stretched by expanding space and bent by the gravity of things you will never see. But it has not aged, not by a second, not by the smallest measurable fraction of one. The photon that left that star and the photon arriving in your eye tonight are separated by the entire history of your species, and by no elapsed time at all. That is what sits on the other side of the wall we cannot cross, not a shortcut, not a destination, a perspective in which the journey and the arrival are the same event. We will almost certainly never reach it, but we can understand it, and understanding it from down here at 1 second per second may be the most extraordinary thing our slow, heavy, light-trapped species has ever managed to do. Somewhere in all of this, it would be easy to feel small, fenced in, held down by a wall none of us will ever climb. But sit for a moment with what that wall actually gave you. Your clock and your mother's clock still agree. The friend you messaged this morning is living inside the same hour you are. When you say right now to someone, they know exactly what you mean, and they know it only because neither of you ever left. That shared present is not a small thing. In everything we've walked through tonight, it's the rarest arrangement of all. Every traveler in this story had to give it up. They bought the stars, and they paid for them with everyone they loved. We stayed slow, and staying slow is the only reason we get to keep each other. Thank you for climbing all of it with me. If it meant something, a like and a subscribe are how I'll know, and there are quieter, stranger journeys still waiting. Sleep well tonight. You're still moving, 1 second per second forward alongside every single person you love.